All right, welcome back to week 3 of Physics 325. This is the last video of the week. In the first video, we looked at a microscopic picture of what causes light-matter interaction, and we looked at it macroscopically in lecture 2. Both of these involved somewhat sophisticated models, right? We looked at this Lorentz model in the first video, where we had atoms that are being shaken around by the electric field. In the second video, we looked at the material properties, epsilon and mu of a material, and found out how electromagnetic waves interact with that interface. We found a few interesting things. We found that the index of refraction is complex, and we found that there are special angles. There's angle of reflection, which is equal to the angle of incidence. There's an angle of transmission, which is related through Snell's law. And when we looked at the amount of light that got through with the Fresnel equations, we found that there's a magical angle, Brewster's angle, for which the reflection totally disappears for one of the angles. And there's also this phenomenon of total internal reflection. So we're going to go through the implications of all these points in today's lecture. So let's start. Okay, so we found last time that there's this complex index of refraction. So before we go any further, let's just remember that what light does in an interface. If we have lambda, we have a wavelength lambda, and I won't use green. I learned last time that when you have a green screen with a green marker, you get some funny results. So I'll keep that one down there. And we have light of a given wavelength. Say in vacuum, it goes to a more dense medium, say glass, n equals 1. And what you'll find is the wavelength bunches up, right? Lambda in vacuum goes to lambda naught over n here. And really what this says, we have this term, k times z in our exponential. So we had, let's just write it out, we had this phase term, e to the I kz plus omega t, which is the phase evolution of the electromagnetic wave. And if we look at this term, it says 2 pi over lambda times z over lambda, right? So it's rather 2 pi times z over lambda. So the number of wavelengths that we go times the phase per wavelength. So what this is actually saying is that when we have lambda going to lambda naught over n, this is equivalent to going 1.5 times, or n times in this case, longer in vacuum, right? That's what this bunching up of the wavelength is. We've accumulated the same amount of phase, right? So this term, this k times n, z, will now go to n times whatever it was in the vacuum times z, right? Because lambda goes to lambda over n. So 1 over lambda goes to n over lambda. And sometimes we think about it this way. It's this k, this vacuum wavelength per phase, times n times z. And this is the effective length, the optical path length that light has to go, right? It's like it traveled in vacuum n times longer. And what if we can think about things more generally? What if it's not just a slab of glass, but what if it's a continuously varying thing? We can still generalize this optical path length, OPL, which usually is called eta, as just integrating this continuously varying index of refraction along some path. Let's call it a path. And this is the optical path length. Okay, so we're actually going to hear about this, I'm excited, in one of the presentations about Fermat's principle and the principle of least action. It turns out that nature chooses a path for light such that this term, whatever it is, this optical path length, is at a minimum. Very, very neat stuff. But for us, in today's lecture, all we're going to use is the fact that this kz that we had in vacuum goes to nkz. So our plane waves, e to the I kz, will now be e to the I nkz minus omega t. Okay, so we have a reduced wavelength in the vacuum, which leads to a different form for our plane wave. And what we found in lecture 1 is that somehow the index of refraction was complex. So what does that mean? What does it mean to have a complex index of refraction? Well, let's just plug it into our new definition, our new and improved plane wave. We get E naught e to the I nk, which is I is now n real plus I times n imaginary, whatever those are, times k, what it would be in the vacuum, k as it would be in the vacuum, minus omega t. And we get, this is E naught e to the let's just write it all out, real k naught z plus I times I, that's negative 1, minus n imaginary k naught z minus omega t. So we can factor that out as a normal plane wave, nr k naught z minus omega t, all times I, plus this real term now, which is now an exponential decay, and imaginary k naught z. So we have a complex index of refraction. We actually have an oscillating part as before, but now this complex part, this imaginary part rather, leads to an exponential decay of our field. Okay, so what does this mean? We have our normal propagation, which is our real part, right? And this is actually the velocity of the wave, right? Because remember that if we write this term out here, anything that satisfies the wave equation, way back from week 1, had to be the form f of z minus v times t. So here we can factor that out. We're going to factor out n real k naught times z minus omega over n real times k naught t. Now in vacuum, we knew that omega over k naught is just c. So this is z minus c over n times t, n real times k naught. And we got our velocity, which now we actually call the phase velocity. We don't even just call it the wave velocity anymore. We're going to call it the phase velocity because it is the velocity of a phase front as it propagates through space. So if we have a single plane wave, the velocity of it is c over n. The real part of the index of refraction is what we've been calling the index of refraction all along. The imaginary part of the index of refraction, on the other hand, will give us the absorption, the attenuation of the field. So in fact, it's going to do something like this as it goes through an interface. Not only will the wave length reduce because of the real part, it will actually get smaller in amplitude and die out exponentially, and that's governed by this imaginary part. Okay, so let's dig into this a bit deeper. In the course, we've mentioned this a few times, that we don't often measure the field, we measure the magnitude of the field squared, the time averaged intensity. So let's look at the intensity with this knowledge that we have here about the index of refraction. So if you remember the definition of intensity before, 1/2 epsilon naught c times the magnitude squared of the electric field, we can plug in our form, our plane wave. Oops, I erased it, might as well write it again. We can plug in this equation, 1/2 epsilon naught c times E naught magnitude squared e to the I. We can plug in our real part, and real kz minus omega t, and this exponential decaying term minus an imaginary k naught times z, and we take the magnitude and square that. The magnitude of this thing is just equal to 1. It's just a phase. So we're going to get 1/2 epsilon naught c times just the amplitude of the field squared, but this term is going to survive because it's real. Taking the magnitude of that is going to give us e to the minus 2 an imaginary part times k times z. And this is what the intensity was to begin with. And we have an exponentially decaying intensity as soon as it enters that medium with this term out front, n imaginary kz. Okay, so when we do that, we can plug it in. And often we just write it in terms of the original intensity. Notice the original intensity is what we get at z equals 0 here, okay? This is known as the Beer-Lambert law, or sometimes just Beer's law. So here's Beer's law in beer. Of course, it has to be. And what this tells us is that basically you get an exponentially decaying. The ratio of the intensity as a function of position to the original intensity is just this exponential decay with alpha. Here we see in this formulation that this is just alpha here. 2 times n imaginary times k. All right, it's hidden in there. I better actually write it more legibly. It's not good to hide your equations in the middle of a lecture. N imaginary times k naught, which is 2 pi over lambda. All right, and you can use this to quantify different substances. And just for some nomenclature, the optical depth is how far you have to go before you've decayed by 1 over e. So here the optical depth is 1 over alpha. Just nomenclature you might hear. Okay, so we're gonna go on, and we're gonna talk about how this relates to the stuff we did in lecture 1 about the susceptibility. Remember we had the susceptibility. It had a real part and an imaginary part. But for now, let's just use the fact that, let's just leave it in terms of n, and note that we could relate this function, 1 plus chi, which gave us the index of refraction, to the index of refraction this way. And if chi is small, as it often is, we can write it this way. So that the real part of the index of refraction is just 1 plus 1/2 times the real part of chi. And the imaginary part is equal to 1/2 times the imaginary part of chi, right? So we can plug it into what we had before. Let's just grind it through, and we're going to get e to the e naught, as we had before. We had our real part of our index of refraction, which is 1 plus 1/2 chi real, times, that's n real here, times k naught z minus omega t, times the imaginary part, which is minus chi imaginary over 2 times k times z. Probably pushing the limits of what we can see here. Okay, so let's just grind that out here. And note that we can factor this term up into 2 points as well. So we can have e naught, let's just pull out this term here, e to the I k naught z minus omega t. That's just what we had with the plane wave, times e to the I, real part of chi over 2 times k naught z, times this decay term. All right, we have 3 terms here. So let's explicitly write that out. We've actually factored this into 3 terms. And we can identify something interesting here. The first term gives us just the normal vacuum propagation. As if this was in a plane wave, if this was not in matter, this was not in stuff, pretend we're going through a piece of glass with a given index of refraction, we just have this first term out here. The effect of this is to do 2 things. It adds a phase shift, which for a sine wave is just a delay or an advance as it propagates. And it also adds attenuation. So the first term just tells us what the wave would have been were there nothing there. Then we multiply it by a phase shift, a phase factor, which is going to shift it back or forwards. And we also include attenuation. So writing it this way, we can kind of really see that factorization of the 3 effects, just the normal propagation, the additional phase shift due to the medium, and also the attenuation. And on your assignment 2, you get to calculate this for a specific case of, I think, a cloud of rubidium atoms in this case. Now I can't help but just paint this picture one more way. We're going to rederive the same thing just so we can see it in a different light and build up even more intuition. Okay, so we'll leave chi as it is. We'll leave chi as it is. It's real plus an imaginary part. And we'll just write out the wave in terms of chi. All right, so let's factor out the chi part, but leave it as imaginary. So this last term actually has a real and imaginary part. It includes both. And we'll use the fact that for a very small chi, for very small y, for example, we have a Taylor expansion of the exponential that goes like this. Now, if not only chi is small, but also k times z times chi, we can use this approximation. So think about it as like a very thin sheet of substance. We can use this approximation. And if we do that, we see the following form of the electric field. We just multiply it out. This factors into 2 terms. Okay, it factors into the term on the left plus the term on the right. What is the term on the left? Once again, is that vacuum propagation. The term on the right is a separate plane wave. It's another plane wave that's also going through vacuum, but it has been phase shifted. It requires a phase shift and an amplitude change depending on where it is. Okay, so we can actually physically get an intuition for this. What is happening when light goes through matter? Well, it's not that so much that it gets absorbed and re-emitted or anything like that. Really, this picture is saying that it just goes directly through, and the dipoles themselves are emitting a secondary field, and what we see is a sum of these 2 fields. Okay, so we have the original field plus the field due to the dipoles. So one last thing I want to say about the complex index of refraction before we move on, and that is about transparent materials. So remember what we had. We plotted the we found chi had this Lorentzian form, and therefore n had this Lorentzian form, and it looks like this when you plot it. Now, if you look at the functional form of this, it has a real and imaginary part, and the real part goes as 1 over the detuning. Remember, this delta is how far away you are from the resonance. The imaginary part, which is the absorption, goes over 1 over the detuning squared. So near a resonance, you can be completely dominated by this absorption. But if you go, say, 10 times the width of that peak away, the dispersion is reduced by a factor of 1/10, whereas the absorption is reduced by a factor of 1/100th. Go 1,000,000 times far away, then it's reduced by a factor of 1,000,000,000,000, the absorption, whereas it's just a factor of 1,000,000 for the dispersion. Now, if you have very, very dense materials, the absorption can be really, really, really like insanely high for near resonance. But a lot of materials have those resonances in the UV, the ultraviolet, that we can't even see. So that absorption, that tail, that 1 over delta squared term, has completely vanished by the time it gets to the visible. But this kind of slow decay, comparatively, of the real part means that we still see significant phase shifts. This is precisely why we can have transparent materials that strongly bend light. They have a large real part of the index of refraction, so they can refract light strongly, but you get next to no absorption. This actually allows me to have glasses and correct my vision. For not only does the light rays get bent the right way, but I can see through them as well, which is a bonus feature, I think, for glasses. So this is one of the properties of the way that the real and imaginary parts of this function are related. They relate in such a way that far away from resonance, we only really need to care about the real part. So that's the index of refraction, all we wanted to know about it. Let's move to the next part, which is the Fresnel equations that we discussed in video 2. Now, here's the Fresnel equation for an index going from an incident material which has a lower index than a transmitted. For example, going from air to glass or water. This is what these Fresnel equations are going to tell us. Remember, there's 2 polarizations, which is the wiggling direction of the electric field. So if we're coming in at an angle like this plane of incidence, which is horizontal here, as we're coming in, we have the P polarization, which is wiggling perpendicular to that plane of incidence. That's the S polarization, the S polarization, which is wiggling perpendicular to that plane of incidence. And we have the P polarization, which is along the plane of incidence this way. And the amount that gets reflected along this way is RP, and the amount of light wiggling this way that gets reflected is RS in this curve here. So from this we can see a few things. We can see that, first of all, the reflectance goes to 1 as you go to 90 degrees. So even things which are not good reflectors, such as this piece of cardboard here, it becomes a better and better reflector. I don't know if we can see this. I'm going to try to make it happen. It becomes a better and better reflector the more glancing of an angle you get, right? So it has to be very smooth to have a constant angle here. But if you have a smooth surface of like black plastic or something like that, it will look like almost like a perfect reflector if you go to very near 90 degrees. Okay, that's the first thing. Another very interesting thing is that the P polarization at some magical angle here vanishes. All right, it vanishes at some point. That means 100% of it goes into the material. The reflectance goes to 0. And when that happens at what's called the Brewster angle. So let's first build up a bit of intuition on why that has to be or why that could be, and then we'll calculate the angle. So if we remember, we had this picture of light, that light is wiggling atoms and they're emitting dipole radiation. And at the interface, we're wiggling a bunch of dipoles and they're all emitting their own dipolar field like this. Here's our crazy dipolar field. Notice something special about this. Here the dipole is moving up and down. And the reason that we were able to have a polarized coherent beam that's spherical is that we had to have a zero crossing. So right along the direction of the motion of these this wiggling dipole here, the field goes to 0. It vanishes. Okay, so let's look at light at the interface. So here's light at an interface. We have our incident wave, and it's wiggling all the atoms, and we're generating a reflected wave and a transmitted wave. And as we oscillate these atoms, we can see that we're wiggling them, and along one particular direction, those atoms cannot re-radiate. Okay, so along a particular direction that is perpendicular to the direction of their wiggling, the atoms cannot re-radiate. So let's think about what's going on at the interface, right? We have our incident wave that's oscillating these atoms. the light that's reflected has to come out of that reflected angle that's related by the law of reflection, and that same wiggling is generating the transmitted angle, right? Let's look at the perpendicular part, the direction of the electric field of that transmitted angle, which is created by the atoms. And notice something. For a particular angle, that electric field is going to be along the direction that the reflected angle is supposed to be. It's going to be transverse, transversely wiggling, but in the direction that that reflected field is going to be. Right? Those dipoles cannot, therefore, if they're wiggling this way, they cannot create an electric field. We can go past it, we can get a reflected field. Before it, we'll get a reflected field. But right at that particular angle, we will get a vanishing reflected field, because the dipoles that are oscillating will not be able to produce light in that direction. Okay? So let's calculate the condition for Brewster's angle. So we have our field, like that, and it has its own electric field vectors this way. We have our incident light this way, and for our Brewster angle, that will be directly in line with these electric fields, with the direction of the electric field of the generated fields by the medium, right? That's supposedly creating this reflected field. So we have our incident angle, our reflected angle, which is equal to the incident angle, and our transmitted angle. And for that particular case, where these atoms are wiggling here in such a way that the dipoles are directly wiggling along this reflected field in creating this transmitted field here, then we will call that Brewster's angle. So this is theta b. And for the law of reflection, that's also theta b here. So we have a 90 degrees. If I have a line here and I add up all the angles, that's 180 degrees worth of adding, right? So let's just add up the angles. We have the transmitted, so we have theta t plus 90 degrees plus theta Brewster, that's whatever this magical angle is here, should equal 180 degrees. Okay, we'll get the 90 over to the other side, right? So this happens when theta transmitted is equal to 90 degrees minus theta Brewster. Let's take, if this is true, I can take the sine of both sides and multiply, say, by nt. So I'm going to have nt times sine of theta t is equal to nt times sine of the other side, 90 degrees minus theta b. Okay? But we know these terms from Snell's law. This is equal to n incident times sine of theta incident. And theta incident here for this particular condition is theta Brewster, is equal to n2, which, whoops, I should just call, should be consistent, n transmitted, sorry, times sine of 90 minus theta Brewster. What's sine of 90 minus theta? It's cos of theta. Cosine of the Brewster angle. So that sine of the Brewster angle over the cosine of the Brewster angle is equal to, well, that's what we call the tan, right, of the Brewster angle, is equal to nt over ni. This is the definition of the Brewster angle. So whenever this condition is met for this particular theta, such that arctan of theta is equal to arctan of nt over ni, we're going to have a Brewster's angle. That reflection will vanish, and that's happening right there. Okay. Okay, here we are in the Elliott wing, and we're looking at the reflected light. I have a polarizer which blocks one polarization and not the other, and as I rotate it, the light disappears for a particular angle, corresponding to p-polarized light at the Brewster angle, which from here looks to be about 60 degrees for this particular floor. So that is the definition of the Brewster angle. Let's look at another bizarre phenomenon that we talked about. All right, let's go from a more dense to a less dense, looking underwater into air, or from glass to air, hopefully not looking from glass to air. We get a Fresnel equation which looks like this. We still have a Brewster's angle, right? Because we can have a tan of anything. Arctan of like infinity, negative infinity is defined. It's negative pi over 2. So tan's very forgiving. So we're going to still have a Brewster angle, no matter what the ratio of N1 and N2 are. But we also have a new thing that happens. We have this critical angle, which is actually what it's called, the critical angle, where we have total internal reflection. The reflection goes to 1 and it's pinned there. It stays there. Okay? So what is a condition for this total internal reflection? Well, we have Snell's law. It says that N incident times sine of theta incident is equal to N transmitted times sine of theta transmitted. But if this one is bigger than this one, we're going to get a picture that looks something like this. We're going to be bending further and further away from the angle of incidence. I'm shining out, this is say N incident and N transmitted here, so I'm going this way. I'm picturing this as like water or glass or something like that. There's going to be some angle for which this is as big as it can possibly be. The biggest that sine can possibly be is 1. And it can't be any bigger. It's as big as sine will get. So at that condition, this is where we get total internal reflection. After that, if we have any angle that's more shallow than that, we'll have a reflected field. We'll only have a reflected field. Note that we actually always had a reflected field here, but for theta bigger than that magical theta, which we're going to derive in a second, the only thing that remains is a reflection. So what is that? Well, if we simply set this to 1, the biggest that it can be, that's our definition of our critical angle. It tells us that Ni times sine of that critical angle, whatever it is equal to Nt. We get that sine of theta critical is equal to Nt over Ni. Similar to the Brewster, easy to remember, right? Similar to the Brewster. For Brewster angle, tan of theta Brewster is Nt over Ni. For the critical angle, sine of theta critical is Nt over Ni. Okay? So that gives us the critical angle for total internal reflection. Anything beyond that will be mirror-like. It'll be completely reflective. Here's a picture of an underwater picture of a swimmer. Notice that when you get far away from the camera, the top of the surface behaves just as if it's a mirror. But if you look at the top of that picture there, you can see that you can see out of the water all of a sudden. So there's a cone which you can see out of the water, and everything else is totally internally reflected. That actually allows you to make things like fiber optics and waveguides. So check this out. Okay, so here I have a laser and some pieces of plastic that have a given index of refraction, about 1.5, I think. And we can see a few interesting things here. So first of all, we can see refraction. Right? So if I shine light into this surface, it's coming in at an angle like this, and it's bending. The transmitted ray is obeying Snell's law. We have another interface, which is translated there. We have a reflected beam as well that's coming off this way. We have to shine it down onto the desk, but if you see that, we have a reflected beam coming this way as well. There's even a reflected beam off this surface, which we can see coming through here as well. So we can see quite a lot with that. Now let's look at that transmitted beam and put it into this light here. We see that it does not refract, it goes through. So it stays in this surface here. Let's zoom in on that and see why it is. So we have some curved shape, and as long as the angles aren't too steep, the light will always be in the condition of total internal reflection and will propagate this way. So you can really see that when you have something like this, you can see the beam in there, and as I change the angles, it just kind of stays in, reflects. So one final thing about total internal reflection, when we had that light bouncing around that plastic there, what happens to the field right after total internal reflection? Turns out it can't like abruptly go to 0. That wouldn't satisfy the wave equations. You can't have a discontinuity that sharp in the intensity without a 0 crossing. But what you find beyond total internal reflection is there's a small decay. The field decays along the material and kind of sloshing out and sloshing back in that has an exponential decay. Okay? And it's called an evanescent field, right? So here's a plot of what the field looks like. It's very near. It's only a few wavelengths around the surface. But it's the evanescent field that is permeating and just kind of sloshes in and goes back into the material. So it doesn't decay instantly to 0. All right? That might be an interesting topic for later in the course if we get into hardcore fiber optics. We'll talk about that. But for now, just know that it exists and we have this exponential decay. And if you manage to probe something in that exponential decaying region, the field can leak through all of a sudden. You lose energy, the field leaks across a gap. And this is called frustrated total internal reflection. And here's a picture of something like that happening. The glass, you can see that is experiencing, when you look into it, total internal reflection. But for regions where someone's put their finger there, the light can actually couple through, and you have this frustrated total internal reflection. There's actually a very practical application to this, and that's in coupling waves that are in waveguides or optical fibers, so-called beam splitters. If you have a beam that you want to split into two, you can use total internal reflection, which is going on in the fibers, combined with this frustrated total internal reflection to couple from one side to another. And by tuning different parameters, you can get, say, 70% of the light in one or 30% in the other. And here's one of those devices with a simulation showing exactly how this is done. Okay, last topic for the day. Let's talk about phase shifts. The phase shift upon reflection. So let's start with external reflection. If you look at the form of the reflections, not the magnitude squared, the capital R, the intensity of the actual field, notice that it goes negative at some region. For the S polarization, it's always negative. For the P, it starts negative. What does that actually mean? What does negative mean? Well, if we have normal incidence here, we can just plug into theta equals 0 to these equations. We get this form, and if Ni is less than Nt, we get a value that is less than 0. And we do some mathematical wizardry, or whatever you want to call it, and note that -1 we can also write as e to the minus I pi. Right? So for a sine wave, multiplying it by -1 is equivalent to a pi phase shift. So what this tells us is there's a pi phase shift between the incident and reflected light when we go from a less dense to a more dense medium. And for the S, it always stays negative. It's always a pi phase shift. Interestingly, for the P polarization, after the Brewster angle, it flips. So we can see that from this plot here, that it goes positive at some point. So if we were plotting the phase shift, it would look like this. Here's pi, also known as, I said minus here, should say I pi. If I have 180 degrees and 0 here, S polarization is like that for all angles. Here's theta Brewster and 90. Whereas P polarization will start out at 180 and flip to 0 afterwards. So that's what the phase shifts look like for what's called external reflection, when you're going from air to glass, or even water to glass, when you have a less dense to a more optically dense medium. Okay, so let's do internal reflection now, when we're going from water to air, for example. So in this case, we can apply the exact same reasoning, and we find that at normal incidence, we get no phase shift. When you go from a less dense to a more dense medium, you get a 180 phase shift of the wave, right? This is, you see this like in first year physics with ropes and things like that, and you see it with sound waves as well, like that. If you go from a more dense to a less dense, you don't get a phase shift, right? The phase remains the same, and this is predicted by the Fresnel equations. So no phase shift upon reflection. How about for the rest of the phases? Well, you can actually calculate it. We can just take the argument of these. We can look at the phase. The phase, remember, is just the argument of a complex number. And it turns out when we're doing this total internal reflection stuff, and we look at the region beyond the critical angle, this reflectance becomes complex, which we know now leads to a decay, this exponential decay, like we discussed in the start of the video. And see that for S polarization, we get no phase shift all the way across. Similar to P polarization, we get 0, and then it flips when we go to the Brewster angle. And something very interesting happens after total internal reflection. You get an asymmetric phase shift between the S and P polarization. So they're all shifting in their own way, starting out at their original points and continuously changing even as the angle changes from total internal reflection. So in terms of the intensity, it's all reflected, but the phase of that field is varying continuously as a function of angle. And this is used for some interesting devices we might talk about in polarization, called the Fresnel ROM, for example, where you can actually utilize this to rotate light in a particular way without losing any light. Okay, so these are the applications of the stuff we've covered so far. Okay, so let's summarize. So we had a complex index of refraction that had two parts rather. It had the real part and the imaginary part. The real part gave you refraction and the phase velocity, and the imaginary part led to absorption. There was a Brewster angle. That Brewster angle where the dipoles were not able to emit in the direction that the law of reflection demanded, that reflection vanished. That happened only for the p polarization. That's the only way that you're going to have light oscillating in that particular direction. That was given by the arctan of the transmitted divided by the incident ray. And at that point, reflectance went to 0. Finally, we had this phenomenon of total internal reflection. So for beyond a critical angle given by the arc sine of nt over ni, all the light is reflected. You got some crazy phase shifts after there, but the reflection went to 100%. And that led to an evanescent wave that propagated a tiny sliver above the field. And that's it for part 1 of the course. There's 3 parts. Part 1 was the interaction of light with matter and the fundamentals of electromagnetic waves. Part 2 is phenomenology of optics, where we talk about diffraction, dispersion, interference, and polarization. And part 3 will be instrumentation. So I will see you in a couple weeks, lecture-wise, and soon in class. Thanks.